All right, this device is called a rectifier bridge. Now, this portion of the video is going to take a while, so repeat this as necessary till you'll understand it. So this rectifier bridge was found in the same GM alternator as the diode trio that you previously seen was in. So late 70s, early 80s GM vehicles. And what you can see here are 3 posts, and to these posts was attached the stator of the alternator that produced the AC voltage. And what this rectifier bridge did, it was 6 diodes, 2 diodes per winding of the stator, and they converted that AC signal, which we can't use in an automotive application too often at all, into a pulsating DC, which we can use. So the makeup of this 6 diode arrangement is as follows. The AC came in on these posts, and these copper tabs were 1 lead each of the 6 diodes. Now, these 6 diodes were separated. Now, they're the same diode, but they were separated into what we called positive diodes and negative diodes. Now, the difference was nothing at all with the diodes. It's just which portion of the AC signal it rectified. And the top half was the negative diodes, and the bottom half was the positive. And what I want you to do is, again, repeat viewing this portion of the video as necessary till you understand this. But you want to take a look at this entire aluminum housing here. This was a heat sink. Right? We needed to dissipate the extreme amount of heat found at these diodes because they were putting through at the time 50, 60, 70, up to about 80 amps, I think was the maximum amperage output of the alternators at these times. And they would generate a lot of heat. And you needed to dissipate that heat, so we use these aluminum sinks. If you'll notice, this piece here and this piece here are insulators. So they electrically isolated the bottom half of the heat sink from the top half of the heat sink. And I'll turn it over, and you'll notice as well that the entire back, where it would mount to the back of the alternator housing, was also not touching the heat sink as well. It was isolated from that. So you had 2 completely isolated metal components from each other as well as the housing of the alternator itself. Now you can probably see here that there was a screw holding this to metal case of the alternator itself. This was located inside the alternator. Now this metal case with this screw that was in here, obviously, and that metal case of the alternator obviously being negative, grounded, it grounded this whole section here. So this top half were called or designated the negative diodes. And this bottom half, you can see there was a screw mounted here. You can see the scratch where there was a screw. And if I flip it over, that entire area was insulated against the case. So that made this the positive side of this arrangement. And these 3 diodes down here were termed the positive diodes. So you've got 3 legs here, and you can tell, since we always wanted current to flow out from here going towards the positive of the battery, these 3 guys were the positive, and these 3 leads were the anodes. Now coming back, because now the greater ground was actually the alternator itself, and these were the cathode leads of the 3 diodes on the negative side. So you can look in here and see these black round discs. They were, or they are, the diodes themselves. And you may ask, what were the other sides of the leads of each of these diodes? They were the heat sinks themselves. For checking these was just the same operation as the diode trio. It's just you have to be more aware that there's 6 diodes. And even if you didn't know which way the diodes were pointing, which was the anode side, which was the cathode, you would be able to figure it out by looking just at your readings, because one way you should get very close to the forward voltage bias level that diode needed to begin current flow, and the other way would be just like this with your open, meaning infinite. It could not flow current. Again, as always, in the diode setting, resistor setting, any setting on a multimeter, always check it first. So you put the leads together. We're on a diode setting, as you can see. It should be very, very close to 0 volts. No effort at all to flow current between these 2 leads. So we just begin. You can pick one side or the other. I am putting my lead on this section of the heatsink here, and all I'm going to do is touch the copper. 0.5, 0.48, and 0.5, fairly close. Now you'll notice this one, I pushed it a ways a little bit, because if this copper tab, which is very close to this sink, is actually touching this heat sink, it's going to show 0. It shows something wrong. So these things have been bent a little bit, so you can tell. But so you push that back and just make sure that, and you've got 0.5. Now you just switch it around, and it should be open, open, open. Those 3 diodes are fine. And we do the same thing to the negative diodes. Make sure you got a good connection here. And if you're not sure, just touch it. It should be 0. So I know I've got a good electrical connection here. Right, so I'm going to try to keep my hand out of the way. You switch hands. You do the same operation for the other 3 diodes. So you can see I've got that in reverse bias right now. Or all 3 diodes are bad. It's one or the other if you don't remember how these go. But you can see it's open, open, open. I'm going to put my positive here now. Switch my hands around again. Keep them out of the way. I should have 0.48, 496, 0.496. So these are all silicon diodes, and you can tell one way was infinite, the other way was the amount of forward bias. And remember, that's what we really want to know about a diode. It's not any type of resistance, because that will give you faulty readings and it's kind of meaningless. You want to actually see how good these diodes are and when they actually start to flow. And that's a measure of voltage, not a measure of any type of resistance. Okay, so that's how you simply check this rectifier bridge. And this rectifier bridge is good.